Okay, guys, hi. Let's continue recording these things. I had to record stuff yesterday for my other class, and so they take their final first, so I better get them their study material. And now I'm going to get you yours. I've posted the last final test review, so you have the test review for number 1, 2, 3, 4, and now the difference between 4 and the final has been posted. And then I'm just going through and talking about it is the rest of this. So you can listen to these or watch these videos or not. That's up to you, but I'm providing them at any rate. So we left off in class. I want to start kind of a little bit of an overlap. And when we did leave off in class, we're somewhere between the second and third test. So I don't have these things in the same order, and that's, that's fine. It's just you kind of have to know what you're talking about when you're talking about it and correlate appropriately. So that's where we're at. All right. So let's see what we have here. So the last thing we talked about was this dielectric strength and dielectric breakdown, and I think it was Dustin who said that the dielectric breakdown is what happens when the dielectric fails, and we end up having a so to speak conductor go from the top plate to the bottom plate in our capacitor, and we would just have electricity flowing through that one section because it just couldn't handle it anymore. So what are we talking about? We're talking about a dielectric that is added to a capacitor in the middle. A dielectric's called a dielectric because the atoms and molecules form little dipoles as the E field is applied to them. So we have this plate on top, the positive plate, we've got the negative plate on the bottom. There's a dielectric in the middle. Let's see here, we can color it with green. So we've got this green dielectric in the middle. And that dielectric can handle a certain amount of E field, but after a point, it gets to a point where it will break down. The E field, which when that happens, this is the E field, okay? That when that happens, when that breakdown occurs, that E field is your essentially the dielectric strength for that material. Okay, so that's what we call that. I did talk about non-homogeneous crystal structure, microfissures and impurities cause that, and right. So at any rate, that's where we left off. So let's move forward from there, and let's talk about current. So our next thing is current. Once we've got that dielectric broken down, we're going to have current. So current, we call current I, and it is dq dt, or delta q delta t. And that, of course, is on average. You guys understand this because you're taking calculus. We could also get the instantaneous dq dt. So at any point at any time, we can get the instantaneous, not the average, the overall average between time 1 and time 2. This just takes us to a point in time and instantaneous. Wow, I didn't even get close. Instantaneous. Okay. Cutting her short. So, units. I'm sure you guys know that it's 1 amp. And of course, we're dealing with, since it's charge per time, it's a coulomb per second. That's the SI units. And of course, current we're going to find can be done in a lot of different currents, but this is the SI situation. Okay. All right, so we've been discussing a capacitor, and that's makes it easy for us to go through and talk about current at this point. So we're charging a capacitor. Well, how do you charge a capacitor? You go like this, you have your capacitor and some EMF, and that EMF is going to charge our capacitor with a charge Q, but it's going to go up as Q of t. And what we can do is we can say Q of t is something. We already came up with it for a capacitor, and we talked about it in class. The Q max is 1 minus e to the minus t over tau. And then it's easy for us to do the instantaneous at this point. It's actually easier than doing the average. So let's just do that. I of t is equal to the derivative of Q of t with respect to t. And we take that derivative. We end up with Q max divided by tau. And should we put a capacitor tau on there? Let's just leave it as tau. Doesn't matter. It's the time constant for this circuit. And that's our derivative. So we've got this as our primary equation for charge. And this tells us how much current is flowing through the system to charge it up. If you notice, it's going to be a maximum at t equals 0, because at that point e to the minus 0 is 1. We've got our Q max over t. So the most current that we're going to have, by the way, of course, that. The most current we're going to have is I max, and that when t equals 0 is when we're going to get our I max. So right off the gate, if we were to put a little circuit, a switch in here, and we flip the switch at t equals 0, then eventually, gradually, over time, we're really going to get 0 current flow. Well, that's an obvious thing, because this guy will, our C will have a voltage across it equal to our driving voltage, our EMF. So once that happens, we're not going to get any more current, right? The current going from here to here is 0. I equals 0. Okay, well, all that jives. It all hangs together. If we didn't discuss this already, I know we have, all right, in class and whatnot. If I haven't done it in this set of reviews, just trust me, we will be seeing more of this. So I hate it when people say trust me, but I'm saying it to you. Okay, so charge flow. We're talking about current now. So what can we do? We can look at we're not going to get current flowing in a lot of situations. However, we have current flowing when the charged particles are flowing away from a comet. We can see it. But on average, that current is 0 because both the positive and negative charges are going, and there's roughly an equal amount of positive and negative charges, and so then our current ends up being 0. So, yeah, well, whatever. Let's just look at a pipe that would be a pipe, say like water, with flow. However, this time our pipe is a conductive material, and we've got positive Q charges going in this direction. That's our flow of current, because the positive is what Benjamin Franklin decided would be the current. Okay, so we've got our current going. It's got our positive Q, and let's make that a real Q. And that's fine. In real life, what is happening? We've got our area of the wire, and in real life, the electrons are flowing in this direction, and our current is in this direction. And this is the reality of it. Electrons flowing in the opposite direction of the current. So what do we call the things that are flowing? We call them holes. So it's the absence of the electrons. So those holes are bouncing around the other way. Now, I don't know if you guys remember, but we talked about a Plinko machine, Plinko game, whatever. But that Plinko game is the same thing that happens to electrons as they're going this way. They bounce. They hit something, they bounce. Right? They're always bouncing around. Eventually, they get down and they move in a drift velocity this direction. Eventually, this motion's called Brownian motion. For a fellow in the 1800s that came up with it. It's a random walk, they call it. So we have a VD. Don't get VD. You can have VD in your equations for drift velocity. So we have our drift velocity, and essentially I'm going to just write without proof or any of the stuff that we've done in the past. Q and A. Okay, so N. Let's talk about N. What is N? Everybody knows what I is, right? That's our current. Everybody knows what Q is. That's the charge for the actual object. And everybody knows what A is. That's the area of our wire. So what is N? N equals the number of free electrons per volume. Okay, so the number of free or electrons that are able to move around per volume. This is material dependent. Material so some materials will have more than others. Okay, so this N, material dependent. Everything else, well, you measure the current. We can find out the Q. A comes from the geometry of the wire, and then the material that the wire is made up of, that material is what we're that's where our N comes in. Okay, all right, so our current I, then if we were to measure I and we were given our charge, our material dependency of N, the area of the conductor, and the drift velocity, we would have our current. So if you were to put all those things together, you'd have a crazy set of units, but the units on that are amps. Okay, so the area, this area, that area is what we would call the gauge of the wire. So the area equals the gauge of the wire. And vice versa. Now they're they're not, well, area, of course, okay, area equals pi r squared, and the gauge will have a certain number, but that number, you can convert, right? There's conversions from one to the other, and you can get your area and gauges. The conversions are doable. It's not hard. Okay, so current flowing through wires happens fairly quickly. So let's how would we see how fast current flows? What is something that we could do as an experiment to see how fast current is flowing? Well, one thing that we could do is we could flip a switch for a light. Let's make it an incandescent light. which means a filament. A filament that heats up as the current flows through it. Okay, that's incandescent. So we have an incandescent light, and we flip a switch, and that light comes on pretty fast. Okay, really fast. Not quite the speed of light, but pretty fast. So why does that happen? Well, we have a few reasons. The E field starts when we flip the switch, it goes down the wire, and it pretty much travels at the speed of light in the conductor. Okay, so that would be copper. So at C for copper, let's use copper, not nickel wiring, which they used to use, believe it or not, and it's not great. But anyway, okay, so E field travels at C for copper, which isn't quite the speed of light for, it's less, right, than for a vacuum, but that's fine. C for copper. It's pretty quick, right? So that E field travels that fast. So you'd think that we would have our lights come on at that point. However, there's some stuff that throws it down a little bit. The filament itself has to heat up. So I don't know if you guys have noticed, you turn on lights in a cold situation and the light is a little bit dim at first and then gradually gets brighter and brighter and brighter. Well, that's because the filament or whatever the thing is that you're trying to get as a source for light has to heat up. So that's that reason. And then the third thing is we basically have, because the E field is traveling from one end to the other, what that E field does is it causes those electrons to travel, pushing from one side to the other. So the only reason that we have flow is because we have a difference in pressure. So the electron pressure in the circuit that electron pressure is a pressure wave, and that pressure wave travels through the circuit, but at a speed that is much less than c. Much less than c. Okay? So that electron pressure wave in the circuit travels at a speed that's less than that. So yeah, it takes a minute or two. It takes a fraction of a second instead of happening just about immediately due to the speed of light. So we get here and we say, okay, we've done quite a bit. That pressure wave, by the way, yeah, no, let's forget that. Okay, so we have current density. Current density. Well, it's exactly what you would think it was. Well, I guess it wouldn't be exactly, because I would say that that would be current per volume. but it's not. It's current per area. So we have current traveling through a certain area. That's our current density. And we give that the J moniker. What are the units of that? Well, it's pretty obvious. It would be amps per meter squared, SI. And how do we get our total current from J over a certain area? So we've got current flowing through this area. We can have a total area A. What do? Well, we integrate J over that total area, and we've got these little dAs. And so we can do the integral of J dot dA over this area here, and we will get our total current through the area. Okay? So that's what current density does for us. All right? And you're like, great, thanks. Another integral for me to do. However, J, the nice thing about J is the units of it are the perfect units, so that we can say that there's a proportionality constant, and that proportionality constant is sigma to the E field. And sigma then is called the electrical conductivity. So we've got our electrical conductivity, and we can rewrite it. If you're looking for your electrical conductivity, you can just say that sigma is equal to J over E. And we've got our sigma, and everybody's happy. So that's awesome. And that is electrical conductivity. Now, stemming from current density, by the way, well, we can rewrite the equation as E being proportional to J. Well, what's that proportionality constant? Well, it's actually obviously 1 over sigma, right? But we could call that a different name, and here's why we do it. I'll tell you in a second. But we call that rho. So E equals rho J, and that rho is our resistivity. I gave up on that one. Sorry. Resistivity. And of course, rho is equal to 1 over the electrical conductivity. So we could write that as rho is equal to the absolute value of E over our current density, J. Current density. I'm going to just tell you, I want to have something on the test that is current density, okay? There will be a current density problem. I want that to happen. So I'm not sure how or where or why, but current density is going to be on that test. Okay, so without further ado, we can say that. Now, here's the thing. The units, I didn't put down units for the electrical conductivity. Maybe I should do that. Let's put the units. Amps per volt meter. That's our units there. Here we've got our resistivity. Resistivity is actually in ohms meter. And it's the same thing as 1 over sigma. But if you notice, that would just mean voltmeter over amps. Well, a volt over an amp is an ohm, right, from Ohm's law. And then there's our extra meter right there. So it totally works out. Volts over amp is an ohm. And so here I'm just going to say 1 ohm is equal to 1 volt per 1 amp. But yeah, that's essentially Ohm's law. So that has to be our unit. And that means that the conductivity then is the inverse of it. So it's an ohm, inverse meter for conductivity. Okay, so let's move on. Remember when we said that our drift velocity was materially dependent, and it's material dependent on the amount of free electrons? Well, there's a few other things that get involved, right? How many impedances are there? How many times are these things going to go through and hit something as they're trying to go down? How many times are they going to hit something? How many inner obstacles are there as on its way to wherever it's going? That's also materially dependent, and all of that tells us that our resistivity, rho, is materially dependent. So rho some materials are conductors. They don't have a lot of resistivity. Some are not conductors and have a high amount of resistivity. Okay, so dependent on material. All right, kind of important. Let's do this one and this one. All right. What else is rho dependent on? Well, rho of temperature. And that equals our rho naught times 1 plus alpha times delta T. Instead of writing delta T, I'm going to write it out for you guys. So you know that what delta T really is, but I'm telling you, every single time you see delta, I've said this 1,000 times, I'm going to keep saying it. Delta T just means delta T at some point, which are our final point, and our initial point, okay? Well, our initial point, T naught, is the resistivity rho naught. So whatever the temperature here is, when we're at that temperature, whatever our resistivity is at that point, this is our reference point. Okay, so we've got our x here, this would be our x value, and this is our y value, okay, at T naught. Okay, so we can increase as T goes up or down. This is our equation, and so we are temperature dependent. So what is resistance with respect to resistivity? Oh, with respect to, I'm being redundant. Not for the first time. What is resistance with respect to resistivity? So we can do it. We can create, so we have some material, we know the resistivity of the material. We've taken a section of that material, we've formed it, and we're going to connect a wire to it on one end. We're going to connect a battery to it, and then we've got the wire going in the other side. There's a cross section of this wire A. Of course, this is the positive, this is the negative, so our E field is pointing in that direction. Our current, and by current, I'm going to say our current density, J, is going in that direction. Well, if our current density is going in that direction, then our current has to be going in that direction. So we've got all of those things happening. Let's call this point, what are we going to call that point? B. We can call this point A. And the difference, or the voltage difference across that from point to point, is VAB. And VAB is equal to our V battery. Or we can just call it our EMF. Let's call it EMF. All right. So we can start looking at all of the equations that we've built up so far. So we've got E equals voltage divided by L. We know what, and this is our E field. We know what our battery is, and that's just our voltage across the resistor. So we've got that. We know that our current density is equal to our current divided by our area. And what else? We can write down E equals rho J. I'm taking that from right up here at the top of the page. And we can put all of those things together and say that V over L is equal to rho times I over the area. Okay, so we've done this. Now we can rearrange that a little bit. V equals rho times L over the area times I. Well, does this look like something? It looks like something. It looks like Ohm's law. And if we say that that really equals R times I, which is Ohm's law, then we know our resistance is the resistivity times the length of the object. Here's the length, L. Didn't put that on there, but I am now. So we've got our length L, we've got our area, cross-section area of the material, and that is our resistance. Okay, so this is the relationship with respect to each other, in fact, because we could take the resistance multiplied by the area divided by the length, and we'd have our resistivity. So either way, we can go forward or backwards with that. And we've seen Ohm's law. Ohm's law. I don't think it's the first time we've seen this this semester. But V equals IR. Okay, so that equation is huge, all right, by the way, in electronics. If you're going to be doing electronics, V equals IR is extremely your friend. And let's talk a little bit about that. Okay, so materials that behave as V equals, not all materials behave this way, okay, but V equals IR, if they behave like this, which most of them do, and literally most of them, but every once in a while some don't, we're not going to look at any. V equals IR is something that is, you can take it to the bank on this test. Materials that behave like this are called ohmic. So, ohmic materials. Keep in mind, ohmic materials are very, well, just like every other material, they are temperature dependent, okay? So the fact that we are using this, by the way, you can multiply and divide by L over the area, the length over the area, and you'll get this equation. Okay, so you can just take the equation up from up above for resistivity and do that, and you'll have this equation. And being temperature dependent does not make something non-ohmic, okay? So this equation does not infer something is not an ohmic material, because all materials are temperature dependent. So to one degree or another, their temperature dependence, how much they're temperature dependent, comes in with this constant alpha, and that alpha constant is definitely material dependent. So some materials are greater and some are less than depending. So, on a bunch of stuff that I don't want to get into. Nobody wants us to get into that. So, energy and power. Let's shift a little bit of gears. All of these things are built on each other. But energy and power, let's do a little bit of that. So we have, I don't know, you're running current through a resistor. So we've got, oh, you know what I want to do? I want to use our new resistor. Here's our resistor. I don't have to draw the whole thing. We've got current running through our resistor. And we've got a power loss. Why? Because that resistor is doing nothing. It does nothing but slow everybody down. What a jerk. Get off the road. No, what it's doing is it's taking energy out of the system, okay? And it's just throwing it away as heat. So it radiates heat, electromagnetic radiation, heat, okay? Infrared, typically, unless it gets to be visibly hot. And then maybe even hotter and goes into the ultraviolet, okay? But, so it could technically do that. So this thing's radiating a bunch of energy away. Well, what does that give us? That's power loss, okay? And we're not gonna go through and derive everything again. Our power loss is equal to I squared times the resistance. So we square the current and we multiply by the resistance and we have our power loss. We can do some things with power, and we can apply Ohm's law, V equals IR, and we can come up with other equations for the power. And this might be, again, power loss, but you have to be careful. Here's my advice to you guys. Only use this one for power loss, okay? Because you're going to mess up if you start using some of the other ones. It's not... You go specifically to the resistor. Maybe there's 4 or 5 resistors in the system. And this is resistor number 4. You're going to just say, what is the current through number 4? I'm going to square that current. I'm going to multiply by R4. If you try and get clever and do other things, you're going to make a mistake. I guarantee it. I've done it. It just doesn't work out. So when you want to know the power loss of a certain resistor, do the power loss of that certain resistor, okay? Otherwise, you're going to be considering a lot of other stuff that that's not going to work for you. So, but that doesn't mean that this isn't applicable, and that can definitely be your power for a circuit. And we also have then power equals our current times our voltage. Now, this one is more like power supplied. Okay? So we're given a voltage, we got a source of voltage, we've got some current flowing I, which we can do all the calculations, figure out what I is, and our voltage power supplied then is that current times the voltage. Okay, so that's why I say, you know what, just you can figure out your power supplied, you can figure out your power loss, and your power loss for, I don't know, maybe you only have four. You've got four resistors. Well, your power, your total power, which might be the power supplied, is equal to the power loss of 1 plus the power loss of 2 plus the power loss of 3. I think you guys get it, but this is a tricky thing, okay? It's tricky. So keep that in mind. All right. This, by the way, comes from the work done per time. So we talked about it. Gosh, I'm just going to write it. Some amount of charge with a voltage over some amount of time. Okay, so that's where this P equals IV comes through, because what is this bit right here? That's I, right? Our average I. So, okay, work done per time. All right. Let's stop there. I'll leave this bit here, but we're gonna stop and continue on in a minute.